Hello, once again. Thanks for joining us on Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley, your host. Good to have your company. On this week's episode 308, we'll be talking sonification. It's not some weird family ritual or anything. It's about the sounds of the universe, and we are going to play a few of them for you today. We'll also be discussing the orbit of Earth and how it's affected our ice sheets. Weird, but probably logical in many ways as well. And we'll be answering questions about gravitational waves, the expansion of the universe, and some of those unknown objects out there that we keep looking for so they don't hit us. And plenty more on this week's edition of Space Nuts. Thanks for joining us.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
We are also joined by the great man himself, astronomer at large, Professor Fred Watson, who is the man behind all the knowledge there is to know about knowledge itself and the universe, just as an aside. Hello, Fred.
I thought you were going to introduce somebody important there. That's. I thought, have we got a special guest? I didn't realise. Well, thank you.
Yeah.
I appreciate being the great man.
Unfortunately, my wife isn't here, so I can't introduce the most important person in my life. Yes. She's at the Dubbo Eisteddfod watching our son do a recital.
Which is fantastic.
My grandson, not my son. Yeah. They would never do anything. But my grandson, he's reciting a poem today. So
excellent.
I'll be missing that, but I'll be watching the granddaughters dance on Friday night. That'll be fun.
And all our listeners in Wales are going to be wondering why there's an Eisteddfod in Dubbo.
We have them it's a big event. You know, our Eisteddfod lasts nearly 2 months.
That's pretty impressive. I don't know how long Welsh Eisteddfods last for.
Yeah. Every kid from every school in the district is forced to is performing.
Encouraged to.
highly encouraged to do.
Very good. Well, look, it'll be a wonderful performance. I'm sure you'll have a ball, and hope the Dunkley family comes up trumps with star of the show.
Oh, I hope so too. Yeah, that'd be nice. Now, Fred, let's move to our first topic, and that is sonification. Now, I'm trying to decide whether to play a sound now or
why don't you kick off with a sound and
let's just fire this one up, because this is something that's been in the news very, very recently. So have a listen to this. Did you hear anything?
I heard the Earth move.
Did you hear anything at all?
Yes, I got the sound effects loud and clear.
I got nothing.
Oh, that's interesting. Oh, well, no, it's good. It's the data sonification of the Sagittarius A-star black hole event horizon.
Wow.
Which is something that we've only had an image of for the last 3 weeks. Is that right? I think it was 3 weeks ago this evening when we had the press release, or maybe 2 weeks ago. I'm losing track of time. With the Event Horizon Telescope, this assembly of 8 radio observatories with their various dishes pointing towards the center of our galaxy, and the data were recorded back in 2017, but now they've crunched it, and what we have is this image of an orange cream donut with 3 blobs in it, which is essentially it's an image of the disk of material swirling around the black hole at the center of our galaxy. And so I might read from the text accompanying it, because this is from the NASA website. Actually, I beg your pardon, it's from the Chandra website. Chandra is a NASA X-ray telescope, and they have kind of pioneered this technology of turning images into sound, and done it, I think, very, very successfully. I hope we might get a chance to play my favourite a bit later on. But the one we've just heard is the sonification The translation into sound of the latest image from the Event Horizon Telescope of the supermassive black hole at the center of the Milky Way called Sagittarius A star. Using a radar-like scan, the sonification begins at the 12 o'clock position and sweeps clockwise. Changes in volume represent the distance in brightness. The Event Horizon Telescope observed around the event horizon of Sagittarius A star. The material that is closer to the black hole, and hence moving faster, corresponds to higher frequencies of sound. This sonification was processed in a special way to allow a listener to hear the data in 3D stereo sound, in which the sounds seem to start directly ahead and then move clockwise to one ear and then the other as the sweep is made. I didn't actually pick that up, Andrew, I'm afraid, but I think it was happening.
What I might do is play it again, because I think because I'm the source, I'm not hearing it like you are.
Hearing it.
Yeah. I'll play it again, and I won't talk over the top of it this time. But now that you've explained what people are listening to, they might get a better understanding of this,
That's right.
the sonification of Sagittarius A.
Did you hear anything then?
Fascinating. I just caught a couple of bits at the end, but that's okay. I've listened to them all pre-programmed.
Yes, before, yeah. To me, it sounds a lot like waves on a beach, actually. Very slow,
I got that impression
waves
too.
on a beach.
But
lovely.
We've done this once before, where they did another sonification, and every sound represented a different kind of object, and that was fascinating. I've chosen one that I think demonstrates that, and this is the Crab Nebula.
All right,
in sonification form. Have a listen to this. That's quite amazing, and it gets intense as it gets towards the middle of that soundtrack, because that's where the most stuff is.
It is, yeah. The intensity of the radiations, the highest at the middle. Can I read the NASA caption for that? Because that's very explanatory, I think. So it's the Crab Nebula has been studied by people since it first appeared in Earth's sky in 1054 AD. Because it's a supernova remnant. Modern telescopes have captured its enduring engine powered by a quickly spinning neutron star that formed when a massive star collapsed. The combination of rapid rotation and a strong magnetic field generates jets of matter and antimatter flowing away from its poles and winds outwards from its equator. For the translation of these data into sound, which also pans left to right, each wavelength of light has been paired with a different family of instruments. X-rays from Chandra are brass, optical light from Hubble is purple. The purple light in the image are strings, and infrared data from Spitzer can be heard in the woodwinds. In each case, light received towards the top of the image is played at a higher pitch, and brighter light is played louder. And that was a lovely sound. I thought that was terrific. I've actually heard that one before.
Right. Well, I've got one more for you.
Good. Okay.
And it is... I chose this one because I know a lot of astrophotographers like to take photographs of various things that are close enough to see, and this is this is the sound attributed to M51. I do like that one.
It sounds a bit troubled to me, does M51.
A bit what, sorry?
Troubled.
Yes.
Of course, M51 is the Whirlpool Galaxy. It's a face-on spiral galaxy, and so what they've done is sonified it in the same sort of way. Should I read it again, Andrew, so that
people understand what they're listening to?
Read the caption for this one, once again, courtesy of NASA. When a star like the Sun begins to run out of helium to burn, it will blow off huge clouds of gas and dust. These outbursts can form spectacular structures. And that's interesting because this is the caption for a different object, and it's not the one they're describing. Good old NASA. So they've got the wrong caption with the right picture.
Oh, well.
Yeah, but so I might not read that because it's not relevant to what we've just been looking at. But I can interpret the images here, because what they've done is combined X-ray, optical, infrared, and ultraviolet images of the M51, the Whirlpool Galaxy, and then done this sweep around radar-like from the center of the galaxy. So what you're sort of hearing as you hear these different notes being played is you're actually tracing out the spiral arms of the galaxy in sound. It's a lovely idea. What a pity they've got the wrong caption for it on the website. Well. Never mind, that's all right. The best laid plans happen.
I should point out that if you do want to listen to all of the sonifications that they've created at NASA, you can do it through the chandra.harvard.edu website. And I've only given you a few. There's M87 Jet, there's the Perseus cluster, Tycho, the Bullet cluster. There are a whole bunch of them. M16, the Galactic Center. And some of them incredibly spectacular to listen to. And I'd encourage you to hunt those down. I might get Hugh to put the link in our show notes. In fact, I can send it to him right now because he's listening and we're live. So I'll just copy that link and send it to him as I speak. And then he'll be able to add that to the show notes for the next episode. So there we go. Fascinating technology, and it sort of gives sound to things that we've only ever really looked at.
Yeah, that's right. And, for a start, that's a wonderful bonus for vision-impaired people to provide a different avenue for experiencing these marvellous celestial images. One thing I was just going to add, Andrew, is that a note to listeners, it's really worthwhile plugging your headphones in and listening to these with headphones, because they have taken very great care with the stereo effects. And certainly my favourite one is that one of the centre of our Milky Way galaxy, which is, it sparkles. It literally sparkles as you play it. And the image in this case is being scanned from left to right. So you get lovely left to right sound effect when you listen to it in your headphones.
Yes. What I'll do is I'll download it, and we might be able to listen to that at the end of the program, because it is a truly amazing piece of music. We'll call it music, but it's the Galactic Center, and this is a sequence that moves left to right on the screen. But we'll do that at the end, eh?
Sounds great. Yeah. Once again, from 3 different NASA telescopes: Chandra, Spitzer, and the Hubble.
Yes, indeed. So we'll do that a little later, but right now we'll take a little break on Space Nuts with Andrew Dunkley and Fred Watson. Time to take a short break to tell you about our sponsor, NordVPN. Now, I've spoken many times about a virtual private network. It's a great way to protect you and your business from a criminal element. And let's face it, crime online is worse than it's ever been. People are getting hacked all the time. They're losing thousands and thousands of dollars. And globally, it's turned into millions, if not billions of dollars. And you really want good quality protection. And you get that with a virtual private network, and the best one you can get is NordVPN. Now, it's not expensive. In fact, there's a special deal for you as a Space Nuts listener. If you want to take advantage of that deal, I'll give you the details shortly. But it is a fabulous way of getting around hackers and criminals. It makes your online data invisible to those people and to anyone else that you don't want sort of jumping around in your cyberspace, so to speak. And it gives you global access. You might want to watch a TV show on a network in another country, and it's probably geo-blocked. I've had that happen a few times myself. But if you have a VPN and log into a server in that country, that's all gone. There are plenty of reasons to have a virtual private network, security probably being number one. But another advantage of NordVPN is it works on all the major platforms: Windows, Mac, Linux, Android, iOS. And with one single account, you can secure up to 6 devices with NordVPN. You can even add it to your router. You can also set it and forget it, so it's always going to be there working in the background, protecting you. And NordVPN is the fastest in the business. Now, as a Space Nuts listener, we have a special URL so you can access NordVPN and grab a very special deal. nordvpn.com/spacenuts, where you can use the special code SpaceNuts to get NordVPN with benefits. It's a 2-year plan, heavily discounted, giving you access to their high speed. We're talking 10 gigabits per second servers, available in 60 countries. With security, as I said, for up to 6 devices. So check it out at nordvpn.com/spacenuts and use the code SpaceNuts to grab this exclusive deal. nordvpn.com/spacenuts. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Okay, Fred, back down to earth this episode or this segment. We're talking about a new study that's been published in the journal Science, and this is really interesting. This is how they've discovered or analysed how the Earth's orbit has affected our ancient ice sheets. And it's in the on the phys.org website, which is a really great place to go and read all sorts of articles and information about what's been going on and what sort of studies have been released. This is a very new one. Now, I suppose we should talk about the old ancient ice sheets, because are we talking about times of much greater ice coverage than we have now?
Yes, that's right. So this is early period. The Earth in its 4.6 billion year history has gone through various stages, which we know about partly because we know about, got evidence on the planet itself for some of these phenomena, but also we understand how planets evolve, at least to a first approximation. So we've got some theoretical understanding. And at one stage, for example, we had what's called snowball Earth. It was just solid ice all the way around. A bit like, I suppose, some of the, the ice moons that we talk about on Space Nuts a lot, the moons of Jupiter and Saturn and the other gas giants. So it's an icy world that we're talking about. And this is the kind of putting the details on exactly how things have behaved. And this is research that comes from Cardiff University in Wales, where they have Eisteddfods as well as Dubbo. And the idea is that you can link some of the evidence that comes from ice sheets, and it's probably from these deep core samples that can be taken, and you can link that with the way the Earth's orbit behaves. Now, 20 years ago, people were very hard to try and link the Earth's orbit to climate change because they were in denial that it's us that's doing the present climate change, but that's subsided a bit now. So an interesting area. And I should add, that the kinds of changes in the Earth's climate that we're talking about, due to changes in the orbit, happen on much slower timescales than anything we're seeing today because of anthropogenic climate change. I think we're probably fairly safe in saying that the last time the climate changed this quickly was after the Earth had been clouted by the Chicxulub asteroid 66 million years ago, because that was pretty quick climate change then too, but for a different reason. So the orbital changes generate differences in the way the Earth behaves in terms of its climate over, longer periods. They're much more gradual changes. And it's been known that the two parameters in the Earth's orbit that affect these ice sheets are the obliquity of the ecliptic, which is a gobbledygook. That's the name of it, the obliquity of the ecliptic. It means the tilt of the Earth in its orbit. So it's that 23.5 degree angle of tilt, but its technical name is the obliquity of the ecliptic.
Never heard that before.
No, well, you can understand why when I was a teenager, some parts of astronomy baffled me. You've got to know the obliquity of the ecliptic. And it rolls off the tongue.
I wish I'd known that when I used to play pinball machines. I used to get tilt all the time.
Yeah, tilt. It's tilt, that's right. Yeah, you could have said, it's the obliquity of the pinball machine. That's what's done it. A good excuse. So that's one, the tilt of the Earth's axis. And the other is the precession of the Earth's axis. So you and I have talked about precession before. It's exactly what happens. If you've got a spinning top and you spin it up, it'll wobble slightly. It'll wobble around. In fact, its axis wobbles in a circle. And the Earth's axis does too, with a period of 26,000 years. Well understood, well established. But that itself actually makes changes because not only is the Earth's axis tilted, but the Earth's orbit is not perfectly circular. So we know, for example, that the Earth is closest to the Sun in January and furthest away in July. It's not by very much. It's 2 or 3%, if I remember rightly. And it's certainly it's not what causes the seasons. Often a misunderstanding that the seasons are caused by the distance between the Earth and the Sun changing. I'm sure no Space Nuts listeners think that because they know the seasons are due to the obliquity of the ecliptic, the tilt of the axis.
Yeah, I was about to say that.
Yeah. But what that means is when you combine those two, the obliquity with the fact that the Earth's orbit is slightly elliptical, it's not perfectly circular, it does mean that there will be some times when the northern hemisphere is closest to the Sun and other times the southern hemisphere is closest to the Sun. And so you get basically slightly warmer summers compared to the other. And that's on a kind of 10,000, probably more like 13,000 year timescale. But the science on this is sort of complicated. And what's happened is that the studies have revealed that over the last million years, if you combine these effects, obliquity and the precession, the wobble, the rotating of the wobble of the axis, the rotation around the precessional axis, as it's called, and you can link these with the waxing and waning of northern hemisphere ice sheets, which is what this was all about. And you find that there are cycles that last roughly 100,000 years. That's over the past million years. But before that, the period that we call the Early Pleistocene, that's the technical name for it, looks as though the ice age cycles, there were cycles of ice ages, but it was the obliquity, the tilt of the Earth's axis that had the bigger effect, giving ice age cycles that were not 100,000 years long, but almost exactly, as the phys.org report says, almost exactly 41,000 years long. And that's been a puzzle. Why hasn't precession played a role in this early period as well? And that's what this Cardiff University study has revealed, that actually precession did play a role in the early period of the Pleistocene. And so it's a complex picture, and to some extent we don't really see the detail in it, but the evidence is now that this is understood. We actually understand why this 41,000 year cycle seems to be dominated by obliquity, but actually precession was playing a part. Maybe I can put it a little bit more succinctly if I don't put it in my words, but actually quote the lead author of the study, whose name is Professor Stephen Barker, Cardiff University, who says early Pleistocene, and that's the period we're talking about before, earlier than 1 million years ago, early Pleistocene ice sheets in the northern hemisphere were smaller than their more recent counterparts and limited to higher latitudes where the effects of obliquity dominate over precession. This probably explains why it has taken so long for us to find evidence of the precession forcing of the climate during early Pleistocene. These findings are the culmination of a major effort involving more than 12 years of painstaking work in the laboratory to process nearly 10,000 samples and the development of a range of new analytical approaches. Thanks to this, we can finally put to rest a long-standing problem in paleoclimatology and ultimately contribute to a better understanding of Earth's climate system. And he winds up by saying, I think very, it's an important statement, this. He says, improving our understanding of Earth's climate dynamics, even in the remote past, is crucial if we hope to predict changes over the next century and beyond. Ongoing changes may be man-made, but there's only one climate system, and we need to understand it.
Yeah, great comment.
Yeah, great comment, isn't it?
Yeah. I am fascinated by how much we can learn from ice core samples, the things we can discover about our deepest, darkest past.
Yes, yeah.
Simply by drilling a hole and taking a chunk of ice out and looking at it under a microscope. I find that quite astounding. And did see something some time ago about Earth's climate and how it fluctuates. I think it was done with ice core samples. Yeah. And they showed peaks and troughs spanning, I think, 11,000 years.
Yep.
And it was showing the heat and cool cycle of the planet. And what's been interesting in the last 200 years or so, funnily enough, is that the temperature rise phase has happened much, much sooner.
Yeah.
And we haven't reached that peak yet, as the other core samples have shown. But the question is, do we stop and start going back down again, or do we keep climbing? And that question can't be answered for another couple of thousand years from what I understand. So we won't be around to know, but it does sort of make you pause that this rate of temperature increase that is natural through ice core samples is actually happening faster because of our intervention.
Exactly.
And that's a bit scary, to be honest.
It is scary, and it's why, there's so much attention now on trying to fix some of the problems.
Yes. Well, it certainly seems to have been the reason that we've had a change in government in this country, That's right. You believe the popular press. Who knows? But I'm glad people are really starting to get more serious about dealing with these problems. This is Space Nuts with Andrew Dunkley and Fred Watson.
3, 2, 1.
Space Nuts.
Okay, Fred, time to answer some audience questions. We've got a couple of audio questions and we've got a text question. And our first question comes from Ireland. I love this accent. I really do. Great question too, of course. That's the most important part. Here we go.
All right, Dunks and Prof Watts. I have a question about gravitational waves and the early expansion of the universe. So, in the inflationary epoch, the universe expanded faster than the speed of light. And I've been told that is because there is no governor on this, or no speed limit on the expansion of space-time. That space-time can expand or contract or be distorted faster than the speed of light. And that's also, I guess, what makes black hole event horizons possible, that space-time is being pulled in faster than the speed of light, and so the event horizon is formed by that. Anyway, the question is, why then do gravitational waves propagate at the speed of light? What is limiting the propagation of those waves to the speed of light if the deformation of space-time is unlimited by that speed? Thanks very much. Love the show. Oh, by the way, it's Brendan in Ireland here.
I knew you'd get to that eventually, Brendan. Thanks for your question. We get a lot of questions about black holes, and we get a lot of questions about gravitational waves. Yeah, he's brought up an interesting point, Fred.
It is, and it's beautifully put too. It's a really interesting question, and I'm not really enough of a physicist to be able to point to the mathematics, but inflation, the idea, that that space expanded at this colossal rate that was certainly not limited by the speed of light, that is really not well understood. There's good evidence that it happened. The idea was introduced in the 1980s to explain one of the anomalies that we find in when we're looking deep into the universe. And it's stuck. It's still accepted that within the first gazillionth of a second of the universe's existence after the Big Bang, it expanded by, I think, a factor of 10 to the 50 is the usual number that's put on it, or thereabouts. Mm-hmm. And that certainly would mean it exceeded the speed of light. And so since gravitational waves are propagated by vibrations in space-time, you might expect them to go at a different speed, but they don't. They are propagated at the speed of light. And as I said, I'm not sufficiently familiar, with the physical processes in order to be able to say why that should be, except that the speed of light is a curious quantity. It's almost like a magical touchstone in the physics of the universe, because as Einstein demonstrated, totally counterintuitive that the speed of light would remain constant, but space could bend and time could bend. But that's what happens. Space and time are flexible, whereas the speed of light isn't. And so it's an absolutely fundamental property of the universe. In fact, it popped out of James Clerk Maxwell's equations back in the 19th century when he was trying to do these calculations. This fundamental number kept popping up, and the speed of light. So my guess is that what governs the speed of gravitational waves is the same sort of physics. And yes, even though the universe as a whole could expand so that the separation between any two given points in it was increasing at greater than the speed of light, that doesn't give gravitational waves carte blanche to go at any speed they like. I think they are dictated by the same laws of physics that dictate the speed of light itself. And that's a glib answer, Brendan, and I'm sorry that it's nowhere near as eloquent as your question was, but it's a very interesting question, and I think that's the bottom line, that the speed of light is fundamental to the universe.
Yeah, and it's the absolute limit. The only thing that goes faster is the universe itself.
Yes, that's the way to put it. That's right.
Yeah, well, it's pretty rudimentary in my brain. That's about as technical as I can get.
As technical as I can get as well, actually.
All right, Brendan, thanks for your question. Let's move on to another question sort of related to that one in some respects.
Hey, Andrew. Hey, Fred. This is Jacob from Phoenix, Arizona. Thank you for answering all my other questions. You were both awesome for that, and awesome for just answering all of our questions. I do have a query, though, in regards to NASA's announcement that our universe seems to be expanding at a faster rate than what was previously expected. I find that fascinating, and I'm a little beside myself on exactly why that would be and how quickly it happened. So I wanted to ask the experts and see if you could maybe give me your thoughts, maybe your ideas on why that might be happening. But I appreciate both of you. I hope both of you are doing well, and I'm a big fan of you all. I basically await new episodes, so I'll be awaiting for this one or any of the new episodes that come along. Thank you so much for your answer and your podcast. Go nuts.
Thanks, Jacob. Unfortunately, we have no answer, so we'll move to the next question.
Great stuff, Jacob. Don't listen to him. He's just pulling your leg.
So what's the answer, Fred?
Well, I think what we're talking about, I'm not really quite sure of exactly what Jacob's question is, but I'll hazard a shot. So what we were talking about, and I think we covered this a couple of weeks ago, the fact that when you do the very best measurements of the Hubble constant, the current rate of expansion of the universe, you get this figure of 73 plus or minus 1 kilometre per second per megaparsec. That's to say that for every megaparsec or 3 0.2 million light years that you go further into space, the recession velocity is increasing by 73 kilometers per second. And yet, if you study the flash of the Big Bang, the cosmic microwave background radiation, and look at the fluctuations in temperature that are in it, which is, we interpret that as the imprint of sound waves, actually, from the early universe. Sound is a big theme in this particular episode of Space Nuts. The bang of the Big Bang is preserved in almost like a fossil in this microwave background radiation. So there's much information in that, and people can use that to predict what the expansion of the universe should be today. And they get 67.5 plus or minus 0.5 kilometers per second per megaparsec. So these two numbers are incompatible. And that's, I think, what Jacob's asking about. Now, I think the jury is still out on why that should be. But you might remember, I think in the episode where we covered that, Andrew, we also talked about this new theory, which it was about changing one of the parameters. What was it? The photon-electron interaction parameter, I think, in our models of the universe. Yeah, that was it. And if you do that, you get, you find you can tweak the expansion, the predicted expansion from the cosmic microwave background radiation, so that it matches what we actually observe. And that filled these scientists, I can't remember where they were working, but it filled them with glee. And then there was this, oh, by the way, there's a byproduct on this, and that's that there's a mirror image universe going on alongside ours,
Right.
which I found very entertaining. I think it's still, that theory is still very much a speculative piece of work, and I'm sure that even the authors would agree with that. But it's the kind of thinking, Jacob, I guess this goes back to your question, it's the kind of thinking that physicists, cosmologists, theoretical astronomers bring to these problems. There's a reason for it. If you've got these two measurements that don't agree, one of them's wonky in some way. We think we're measuring Hubble constant today very accurately, that 73 plus or minus 1 figure. And I suspect that will turn out the tweaking is all done in the interpretation of what the flash of the Big Bang is telling us. And that's what these scientists with the mirror image universe also concluded. So let's see where it goes. I don't have any ideas on the answer, but I think it will be something like that. And it might lead to some new physics, which is what we're always on the lookout for.
Somebody forgot to carry the one. That's
one, yeah.
Probably.
That could be right.
All right. There you go, Jacob. There might be more on this, so we'll just...
Yeah, within the next 40 years, probably, there'll be something new to report.
Yeah. So just stick around.
There's just on that topic, I think they've now switched on the Large Hadron Collider again with after an improvement in its energy levels. And of course, they're looking for symmetries as well. They're looking for supersymmetry, which would be a huge breakthrough if evidence was discovered, because that might lead us to explain all sorts of things like the dark matter, possibly even dark energy. But it might also throw up insights into the kind of new physics that we were just talking about there, this one where you get the mirror image universe. So who knows what is on the future, the horizon. I think it's great.
You never do you?
You never do.
All right, thanks, Jacob.
Space Nuts.
We're going to throw in a bonus question. This is a text question that came in from Ron in New York. He says, according to NASA, only 40% of asteroids larger than 140 meters in size have been discovered. How can they state that they've discovered only 40% of an unknown quantity? Is it that they survey a region of the solar system and count? That's a really good question, Ron. I don't know.
So it is a good question, and it's got a bit of history to it, this, because back in the 90s, I think, NASA was mandated by Congress to discover 90% of asteroids bigger than a kilometre across. Yeah. It might even have been 95%. I can't remember the exact number. And they achieved that. It's the same problem. How do you know you've got 95%? Why isn't it just 12% or something like that? And the reason is that we have a pretty good understanding of the statistics of these objects. There's a sort of spectrum of sizes. The small-sized objects are very, very common. and there are gazillions of them, things a meter across. And in fact, one of those probably hits our atmosphere every day.
Yeah.
But the dinosaur killers, the things that will do global damage to the climate, they turn up once in 100 million years. So you know the sort of statistics that dictate how many objects there are of each particular size. So it's all done on probabilities, which probably sounds a bit dangerous but it's all we've got. And it was, I think, in the early 2000s that NASA was mandated, again by Congress, to discover 90% or 95% of all near-Earth asteroids bigger than 140 meters. And that's what they're doing now. So 40% is milestone en route to that. It's all done in a statistical fashion. And basically, it's not just looking at different bits of the solar system. These are small objects, actually. So they're difficult to find. That's the one good thing about potentially hazardous asteroids. The really dangerous ones are easy to see because they're big. They reflect a lot of sunlight. It's when you start getting down to these smaller sizes, and 140 meters is certainly dangerous if it clouts a city, but they get harder to find. And so what you're doing is you're using your sensors, Pan-STARRS telescope, other telescopes, which are looking at the entire sky, and finding as many as we can so that we improve the statistics. All that will take a big step forward, by the way, in a few years when the Vera C. Rubin telescope comes on stream. That's a telescope, an 8-meter telescope in Chile, which is currently being built, and will survey the whole sky every week, I think, down to a very deep level of faintness. So they will push that 40% number up inevitably, because you find asteroids as well as finding supernovae and neutron stars and things of that sort. That will push that 40% number up significantly, I would imagine.
Okay, yeah. I just realised I missed half of Ron's question because it was hidden. It's on a spreadsheet, so it was hidden until you started talking. But he said, yeah, so is it that they survey a region of the solar system and count these asteroids and then extrapolate that to the rest of the solar system, assuming a uniform distribution? If that's the case, realistically, that distribution is probably not uniform, and we will have a false sense of security that we've got them all. Even one errant asteroid 140 metres across could mean a very bad day for us if blindsides us. Thanks for the great podcast.
Yeah, that's
you probably covered that anyway.
Yeah, that's more or less what we were saying. Yeah, great question though, Ron. Thank you.
I just didn't want to leave Ron in a lurch because he would have heard that half the question was missing. But yes, thank you, Ron. Hopefully, we did. Fred did cover your question, and yes. Feel free to send a follow-up. We do enjoy your questions. Excuse me. And you can send them to us via our website, spacenutspodcast.com or spacenuts.io. There are a couple of ways you can send us questions via the AMA tab, where you can send us text and audio, or on the right-hand side, there's a little sort of semi-inverted tab where you can send audio questions to us. And while you're there, visit the Space Nuts shop and get yourself some goodies. There's lots to look at. Fred's books are there, a couple of other books by some hack as well. You can join Patreon or Supercast. And don't forget our social media, Facebook, where we have an official Space Nuts page, and the Space Nuts podcast group Facebook page, where listeners can get together and chat about astronomy and space science, all sorts of reasons to get online. Now, I was going to do one more thing before we finished, Fred, and that was to play the sonification of the the galaxy. Now, I've been having trouble with the audio today, so this might not work, which means I'll have to figure something else out, but I'll give it a go. We've heard this before, haven't played it for a long time, but it is just a stunning piece of audio. I just love that. And it's just beautiful. And every sound represents a different thing in our galaxy. So there's sounds for stars, there's sounds for, well, every object that you can see in that image. It's beautiful. Really nice.
Indeed, that's right. Yes, so, the stars you can hear twinkling, those are the glockenspiel-like sounds which come from, I think, the Hubble telescope. Chandra, I think, is the thing that sounds like panpipes playing in the background. That's the X-rays. Spitzer, I can't remember what component that is, but it's a beautiful mixture and well worth seeking out on the web, putting your headphones on and immerse yourself in the Galactic Center.
Yes, indeed. And there'll be a link on the show notes to the site where you can listen to all of those audio. And there's video components as well, so you'll be able to actually see what you're listening to, which is what it's all about.
Indeed it is. Yes.
All right. We'll have to wrap it up there, Fred. Thank you so much. We'll catch you again on the next episode.
Sounds great, Andrew. Thank you to you too, and take care, and we'll speak soon.
We will indeed. Professor Fred Watson, astronomer at large, and thanks to Hugh in the studio for keeping us all going every week here on Space Nuts. And from me, Andrew Dunkley, thanks again for listening. Look forward to your company on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.